Yeah, hello and welcome to our lecture series on climate protection. This time is the very last lecture of this summer semester. So this is our timetable. Engelbert Portenkirchner will speak today. A complete decarbonization of our energy system can only succeed if we manage to meet our electricity demands in the future with the fluctuation energy supplies from renewables, from such as wind, solar, hydropower, and so on. Unfortunately, the demand does not always occur at the same time as the supply. In the last lecture, maybe you've heard it from Alexander Thür. He spoke about the flexibilities in the demand side, but we won't be able to do without any storage. Today, Engelbert Portenkirchner, he's assistant professor of the Institute of Physical Chemistry at the University of Innsbruck, and he studies eco-energy technologies in Wales and habilitated at the Institute of Physical Chemistry at the University of Innsbruck. He is head of the working group Battery Technologies. So this technology is exactly his expertise and field of research, which is highly needed for the energy transition. Looking forward to his presentation, Powering Energy Transition, Innovative Materials and Sustainable Concepts for New Batteries. Welcome.
Thank you very much for this kind introduction. Is the audio good? Can you all hear me? Perfect. So it was on Christmas Eve 1968 when the first manned mission to Moon, Apollo 8, entered the lunar orbit, and the picture they've sent to Earth later on became known as Earthrise. This picture that you can see here. And the very recent Artemis 2 mission sent quite a similar picture, among many others, of course. The pilot back then, Jim Lovell, said, "The vast loneliness out there is awe-inspiring, and it makes you just realize what you have back there on Earth." With this introduction picture in mind, I would like to welcome you all to my presentation today, Powering the Energy Transition, Innovative Materials and Sustainable Concepts for New Batteries. My talk or my lecture today will mainly be a long introduction. It's like more than half of the whole presentation will be an introduction. So this is not going to be a scientific lecture that I usually give at conferences. I will not discuss any minute details and changes in various battery technologies. I rather would like to give you an overview what I think is crucial and what is important in this field of research. And then after the long introduction, of course, I will talk just a little bit about the concept how a lithium-ion battery works. I mean, this I have to do, but it will be not too long. And then I would talk about 3 different trends that I foresee in this field of research for the near, mid, and long-term future. Now, trends, as some wise men said, or predictions are always difficult, especially if they are about the future. But nonetheless, I will try to do so, and as we don't know the future, take it with a little bit grain of salt. After this, I would just briefly tell you something about the research that is going on at the University of Innsbruck in the field of battery technology. And then I will finish with some closing remarks. Now, let's start with the introduction. And of course, within this series of lectures, I will start with a few words on climate change and the need for decarbonizing our economy. As you can see here, people holding up many Earths. Many people would like to have more Earths than one, but in fact, we just have one. And all that we are doing has to happen on this one planet, and we have to work in a sustainable and renewable way. And one study that brought this forward very nicely is the Stockholm Resilience Center, and they defined so-called planetary boundaries. And if we are within these planetary boundaries, then we are thriving sustainably. If we are exceeding these planetary boundaries, then not. And unfortunately, what they found out that out of these 9 planetary boundaries, we are already far exceeding 6 of them. And the research and the work that I'm focusing on battery technologies is addressing mainly one of these planetary boundaries, namely climate change. Why? Because climate change is very much interlinked and intertwined with the way how we use our energy supply. For 2 centuries now, humanity was thriving in burning fossil fuels. This picture that I show you here, where you can see women in India that are carrying a coal and a baskets on their head from an open cast mine. This has been the role model for many years, and I hope that I can convince you today that this should not be and cannot be the future anymore. Why? Because, of course, you all know if you burn fossil fuels, you emit carbon dioxide, which is a greenhouse gas, and this leads to the rise in the global temperature. Now, you all are very much familiar with climate change, so I will not talk too much about this, but just a few words let me spend on it. Here you can see the mean surface temperature of the Earth, and you can see since 1850 around, we see a steep increase in this surface temperature. And for all of you who are still a little bit doubting if this is due to man-made global warming, one study that for me shows this very nicely is this one here. You can see in the black curve the measured mean surface temperature of the Earth. And then there are very powerful computer models that scientists have now. And the green curve that you see in this slide would represent the mean surface temperature if we don't account for the carbon dioxide and for the greenhouse gas emission that humanity puts additionally into the atmosphere. And the orange curve that you see there accounts for additionally all this carbon dioxide that society was putting into the atmosphere. And you see that the simulation with the man-made greenhouse gases, they fit perfectly the measured mean surface temperature. So this, I think, is a very good proof that science have understood the whole problematic, and unfortunately, it's really us. It's really our society that is causing the problem. The good thing about this, if we are causing it, we can also do something against it. And this one tiny planet, especially if you look from afar, is somehow fragile. We have to take care of this. And there are many people who actually already do something for it. They go out on the streets, they protest to take climate action and do something against this climate change. Unfortunately, I would have to say that most of the people that are protesting on the streets, that take this issue very seriously and that have the courage to stand up, are not really the decision makers in our society. It always makes my heart cry when I read these numbers like that say that the top 1% of the richest people in the world accounting for more than 66% of all carbon dioxide emissions. And the picture that I choose to symbolize this a little bit, you can see here where golfers finish their round quietly, while in the background a huge wildfire is raging. This picture was taken in the year 2023 in Oregon. There was a heat wave, and the whole of Canada was facing high drought and lots of wildfires. Well, now at the moment, we are also here in Central Europe facing a heat wave. But although many of us are now aching under these high temperatures, don't fool yourself, because this will be still one of the coolest summers that you are going to experience till the end of your life. Just to make the point. Now, let's talk a little bit about what we can do and what we should do. If we talk about climate change, it is clearly rated how humanity is using the energy, how humanity is producing, transporting, storing, and consuming energy. Now, please don't grill me here on the stage. I know for well that we cannot produce energy and then we cannot consume energy. Energy can just be transformed from one form to the other form, but it's just such a familiar term, and everybody of us knows what I'm going to talk about when I'm talking about the production of energy. So I put it under quotation marks, but I will still use these terms. And how energy is produced, has been produced, is like you can see here, some rig operators are guiding a drilling pipe down a borehole for extracting natural gas or oil. But hopefully within the next few minutes, I can convince you that this should not be the future of our energy supply. What about the amount of energy? Human society needs around 140,000 terawatt hours, or around 16 terawatt of actual power at the moment. Where did all this energy come from? Well, as the background image suggested, most of it comes from fossil fuels. Natural gas, oil, the biggest player, and also coal. The renewables, although they are there, but they took only a minor part on this. There are some estimates for the future, and unfortunately, all estimates prophesize a strong increase in the energy demand that we need. By the year 2050, the most conservative one estimate, or can call it maybe progressive one, estimate that we or human society would need at least 30 terawatt of energy. Some estimates go even up to 80 terawatt of power. And when we think back to this introduction slide on the mean surface temperature, I argue that this has to be, there's no other way, carbon dioxide free power generated. Now, if we look here on this graph, the carbon dioxide free power is not that much. We have something in hydro, yes. There is also some part of nuclear, but I'm not going to talk about this because nuclear has its own issues. And the other renewables, they just play a minor part. But nonetheless, I would like you to look at this, and especially on the steep increase in the last years. Especially if we look in the electricity production worldwide, we have already more than 2/3 of the total electricity production coming from renewable sources. So I think that this is really not the picture that we should have in mind for our future, but rather this should be the future, like an offshore wind farm that you can see here in front of the coast of Copenhagen, or that this year will be the future. This is a huge solar power plant in Mexico. What about the readily available resources that we have if we are talking about renewable energies? And this is readily available. That means with the current technology and under current market situations. And you can see that for all different energy sources, being it wind, geothermal, hydro, biomass, or tide waves, the readily available resources are somewhere between 2 and 10 terawatt. But we will need at least 30 terawatt. The only source that I didn't show here is solar. This comes now. Solar has a staggering 10 to the power of 5 terawatt, so 100,000 terawatts readily available energy or power to be harvested and generated. Probably you all have seen this figure before, but I still want to show it. This would be an estimate. The yellow square that you can see here in this slide shows you how much of land area you would have to cover with solar panels, photovoltaic of today's technology. And although I agree that this is a huge area, it's not impossible. It's physically not impossible. It can be done, and maybe, or I'm convinced that it should be done. maybe not centralized like here in Northern Africa, but distributed around the world. Then if I show this graph, people usually tell me about the costs. What about the costs of energy produced from solar, for example? And will our economy be then competitive to economies that are mainly based on fossil fuels? And to elaborate this a little bit more, I would like to bring you this study. This is a very nice publication in the year 2022. And what they did, they looked at the average costs for energy, global costs in dollar per megawatt hour. And they did a very good thing. They did inflation adjustment. So they calculated the price for the megawatt hour without inflation. And there you can see, for example, for the primary energy. So if you have coal and you just burn it and use this energy, there's a certain price, dollar per megawatt hour, and it stayed almost constant within the last 150 years if you do inflation adjustment. And also for crude oil, it's the same. The price is something higher, but it stayed almost constant over the last 150 years. Now, if you take now this coal and you want to produce electricity out of it, of course, the price for the megawatt hour electricity has to be higher. Of course, you have to burn coal, you have to go all the steam engine, you have an efficiency, and you always lose something, so the price has to be higher. But also the electricity that has been produced out of coal-fired power plants stayed rather constant within the last 120 years or so. Then in the 1920s, there came natural gas. And also here we see the same picture. Natural gas started already very cheap, but if you do inflation adjustment costs, dollar per megawatt hour, it stayed constant over the past. And so did the electricity produced out of natural gas. In the 1970s, nuclear started, and it came with the big promise that we have infinite and almost energy supply at no costs. But if you look at this, if you look at the dollar per megawatt hour electricity produced from nuclear energy, you see that it's even a little bit increased over the last decades. And now let's look at wind. Wind became a considerable player in the 1980s. And although it started as the most expensive source for electricity, it continually decreased its cost. And please take in mind, we have here on the y-axis for the dollar per megawatt hour logarithmic scale. So if a linear decrease on a logarithmic scale, it's actually an exponential decrease. And now let's look what happened with electricity produced from photovoltaics. It started very expensive, but it had just such a steep decrease in price. And in fact, if we just look on the last years, we have now electricity produced from wind power is at the moment the cheapest source for electricity that you can get in the world, and followed by electricity from photovoltaics. And then come the fossil fuel produced electricity. So with this argument, hopefully you can see that this, I think, should really be the future of the energy production for our society. And one example that I would like to share with you is this power plant that has been built in 2021 in Abu Dhabi. It has a peak capacity of 1.2 gigawatt, so roughly the amount of a small nuclear power plant. And it was constructed by the company Wilson Solar. And it could offer a price for the megawatt hour of electricity with only $13.5 US. The area that is covered with solar panels is for this plant 8.5 square kilometers. It has 3.2 million photovoltaic panels installed, and the whole planning, construction until the plant was ready to sell the electricity took 23 months. Now, if you want to construct a nuclear power plant with the same capacity, you would need at least a construction time of 12 years. This power plant is reducing carbon dioxide emissions by around 1 million metric ton each year. And this would be equivalent to around 200,000 cars that run on gasoline that are taken off the road. And interestingly for me, is that this bid from Abu Dhabi, from the government, was actually open. So they just wanted the reliable and cheapest energy source that they can get for electricity. And there were many other companies that made an offer, and the cheapest fossil alternative was a coal-fired power plant. And what they could offer was a price of $45 per megawatt hour. So almost 4 times more expensive what photovoltaic could offer. Now, with this in mind, I would like to give you the message that actually the production of energy, the human energy supply, we have the means, we have the technology, and this is to a large extent photovoltaic. So I argue that the scientists, the engineers in the past, they have done a very good job, and they gave us a technology that can supply us with this 30 terawatts that we will need. Our generation now has to solve the next big issue, and that is transport and storage of this energy. So this is my next part of the introduction, storage of intermittent renewable energy. And if I think of energy, I usually don't think of a quantity like X or Y megawatt hours. I consider energy always as a vector in space and time, something like this. Why is this the case? Because usually there is an offset in space and in time where the energy is produced, so to speak, and where it is needed. Let me emphasize this point a little bit more. Let's look into the first dimension, the space dimension. The figure that you can see here shows you the solar radiation per square meter over Europe. And as most of you can anticipate, the highest solar radiation you have in the south of Europe, in Spain, in Greece, even more in north of Africa. But many large consumers for electricity, they are in Central Europe or even in Northern Europe. So you have an offset in space between the location where energy is abundant and where it needs to be consumed or like to be consumed. So this is the first dimension of this vector. The second dimension is the time dimension. And to emphasize this, I show you here for 2 weeks the fluctuations of 3 different power plants in Germany, a solar power plant, an onshore and an offshore wind farm. And of course, as we all know, sun shines during the day, but you want to have light in the night, for example. Or you have these long seasonal fluctuations between summer and winter time. So there's also a difference between the time when the energy can be produced or is most abundant and when it is going to be used. And this is why I emphasize that energy in our society is actually more like a vector property in space and in time. And we have to always take this in mind. And this is exactly the topic about transport and storage of energy. Transport of storage of energy can be realized in different ways. And one way that became very big, especially in the last years, you can see here, this is a liquefied natural gas import terminal in Italy, in Porto Levante. It's actually one of the biggest in Europe. And it's at the moment just unloading a liquefied natural gas tanker that comes from the US. Now, since the invasion of Russia to Ukraine, we closed all our pipelines for good with Russia. And this was somehow prophesized as the role model for the future. But I think this should not be the way how we transport and store energy. I would like to convince you that this is more the way how to transport and store energy. And this brings me to another big point of my introduction to this topic or to this field, the transition to electromobility. The picture that you can see here is one of the first electric cars, a Belgian car in the year 1899, and it was fully packed with lead acid batteries. So it ran on lead acid batteries. Nowadays, of course, all of you know modern electric cars, like here in this picture, the Tesla car and the Tesla truck that ran almost exclusively on lithium-ion batteries. Even more astonishing for me is this picture here. This is the first wireless communication that took place in the year 1920 in Pennsylvania. And you can see this guy there. He's holding a big antenna in one hand. He has a lead acid battery tied around his wrist. and he's talking into a microphone. Nowadays, of course, we all use mobile smartphones for our day-to-day life. So in some respect, we can say for electrical applications, lithium-ion batteries are really the ultimate rechargeable energy storage today. In the year 2024, these are the most recent figures that I got, more than 12 billion lithium-ion cells were sold worldwide. So this means 1.5 lithium-ion cell per person on this planet. And here in the audience, we are now maybe 15 people. So I would bet that we have more than 15 lithium-ion batteries with us. I have at least 2, one in my cell phone, one in the laptop here, and maybe so do you. Where do all these batteries go? Well, 80% of the whole battery production went into the electric vehicle market. And why this is good and important, I would like to emphasize with the following slide. And this is actually not my slides. I took these from Maximilian Fichtner because he had a very nice way how to present this. And I hope you don't mind if I share this with you. You can see here a typical combustion engine. This is a BMW X5 motor, and it has a power of 320 horsepower. And it has around 1,300 moving parts. So it's a very complex, very sophisticated machine that you need for converting this gasoline. In comparison, and this is almost the right size comparison, here you can see an electric engine from the Tesla Model S motor. And it is much smaller. It has a power of 560 horsepower, and it consists only of around 40 moving parts. So it's a much smaller, much more simple and elegant design of converting energy. And what about the efficiency? Well, let's look at the well-to-wheel efficiency. So the efficiency of the energy that is taken out of the well, and then what of this energy can you really use for transportation, for getting your car moving or converting it into kinetic energy, if you want to speak. For the combustion engine, it's 23%. For the electric engine, it's 69%. And another figure of merit that we can look at is the tank-to-wheel efficiency. So the amount of energy that is stored in your gasoline tank in your car and how much of this you can use to propel your car is for the combustion engine 29% and for the electric engine 81%. So this is just in terms of efficiency a much smarter technology. And of course, I have to bring this up. What about e-fuels? Now, many people are talking about e-fuels. So what is if we take the electricity, we produce hydrogen, we take carbon dioxide, and we convert it to an e-fuel, and then we burn it in a combustion engine? Well, the efficiency is as low as 13%. So in my opinion, not a very smart decision. Another slide that should emphasize this, and also this is from the presentation of Maximilian Fichtner, is let's look it in this way. You have one wind turbine with a power of 3 megawatt, and this wind turbine runs for 2,000 hours a year. Now, if you take the energy that is produced by this one wind turbine and you want to power with this your electric cars, and let's say each of these cars drives an average of 20,000 kilometers per year, then this one wind turbine can power 1,600 electric cars. If you first produce hydrogen and then use a fuel cell to drive your car, then the same amount of energy will only allow 600 cars to drive 20,000 kilometers per year. And if you use e-fuels, it's as low as 250 cars. So if we have limited availability of renewable electricity, then I think we should choose the technology with the highest efficiency to get ourselves around. So with this, I hope I could convince you that this should be the future for at least personal transport. Of course, I think going by bike or going on foot is even better way, but for all who cannot do this, electric mobility would be the efficientest way. And this is already going to happen. Here is one exceptional example, and this is Norway. And then you can see that in 2025, 97% of all new cars on the street were electric cars. And not only in Norway this takes shape, but slowly, gradually also in Austria. This is an announcement of the ORF, and this was for April 2025. And there, for the first time, the newly installed electric and hybrid cars surpassed the cars that ran on benzene or diesel. So the battery demand is growing rapidly because of this needed electrification of our personal transport. This is a study that should emphasize this. You can see here in orange the predicted battery demand until 2030. And this also brings us some issues. At the moment, almost all cars are run on lithium-ion batteries if they are electric. But there are some limitations. It is not that we don't have enough lithium on the planet, but the existing mines that we have and the mines that are foreseen to be installed in the next years will not cover this demand. So this is an issue that we have to address, and we are working on this very hard, actually. I will tell you later. And where are these batteries mainly produced? Well, mostly in China. So China is the big player in this development. There are also some production capacities in the US, in South Korea, and in Japan. Europe, unfortunately, missed out on this global trend. This I really have to say. What about the price? The price of energy stored in lithium-ion batteries. And you can see here the blue curve represents the costs per kilowatt hour, and it came down very steep in the last decade. It started very high, it exponentially decreased. And this maybe reminds us of some other costs, photovoltaic. It also started very high, but it decreased exponentially. So we have here two technologies available. One is for the production of the energy that is renewable, that is carbon dioxide free, and one for transport and storage of the energy. And they match very nicely and they match very well. When we think about battery production, if the battery production has such a huge increase and like 12 billion cells, if you remember, then it's not only sufficient if we produce a lot of batteries, but also we have to do it in an environmental and social responsible way. This is a graph that is often used to compare different storage technologies. You have here on the x-axis the storage capacity in megawatt hours, and on the y-axis the time scale. So how fast can you store your energy and how fast can you get it out again? And then there are typically different fields where the various technologies are used. And of course, everybody who works in the field of batteries, they always try to push the boundaries in all directions of this graph. But this is not the only aim and the only goal that we should have. Because when a technology becomes so large as batteries, and social and environmental responsible battery production matters a lot. And one issue among many others in lithium-ion batteries is cobalt. Cobalt can be seen very critical. Here in these pictures, it's just one out of many, is the cobalt mining shown in the Democratic Republic of Congo. And this happens very often under very precarious situations and living conditions. Lithium-ion batteries, they consist of many materials that can be seen critical in terms of the society, but also in terms of geopolitical dependence. There is nickel, cobalt. Cobalt is especially critical because it is almost exclusively mined in Congo, in the Democratic Republic of Congo. But there is also lithium and rare earths. Lithium at the moment comes mainly from Australia, although the highest resources are found in South America, in Chile and in China, and the production of lithium is very questionable. Here you can see a typical production site in the Atacama Desert in Chile, where you have these big evaporation ponds where the water is evaporated and leaves you back with a brine of lithium containing water. That is the typical way how lithium is produced. And also don't forget this supply gap. So even with the existing and planned lithium mines, we cannot power and fuel the transition to electromobility. What would be the alternative? Well, to my opinion, and one of my active fields of research is sodium. Sodium would be very nice. On one hand, the chemistry is very similar. On the other hand, it's just the high natural abundance of sodium. We are talking about 10,000 times higher natural abundance of sodium in Earth's crust and more than 100,000 times more sodium in seawater compared to lithium. In fact, everybody of us at home with using cooking salt has a lot of sodium because half of the cooking salt, sodium chloride, consists out of sodium. And this, of course, is also reflected in the price for lithium carbonate and sodium carbonate. Now, lithium carbonate and sodium carbonate are the main sources for battery-grade lithium. And 1 ton of lithium carbonate costs between 5,000 and 73,000 euros per ton within the last 5 years. So it is always fluctuating a lot, but the prices are always very high. And if you compare this to 1 ton of sodium carbonate, which only fluctuated between 180 and 250 euros per ton of sodium carbonate. And not to mention, the mining of lithium carbonate also creates a lot of carbon dioxide emissions, 30.5 tons roughly per ton of lithium, compared to just 0.14 ton of carbon dioxide per ton of sodium carbonate. Now, this is not so critical because you need very little lithium in one lithium-ion battery. So don't come to this idea that, there's so much CO2 produced in the production of the lithium-ion batteries that we don't have to use this and transition to electromobility. But still, there is a considerable difference between the carbon dioxide emission for lithium carbonate production and sodium carbonate production. Okay, having said this, I finished my very long introduction, and now just very briefly, how does a lithium-ion battery work at all? Let's look into this. If you want to construct a lithium-ion battery, what you need are 2 different electrodes. We also call them cathode and anode. The cathode is typically some metal oxide, like lithium cobalt oxide, which would be a bad choice. A more better choice is lithium iron phosphate that is shown here. And slowly the industry is also moving a little bit into this direction, which is a very good development. On the anode side, this consists almost exclusively out of graphite. So even the first battery that was introduced in 1991 by the company of Sony had graphite as the anode. The battery that you buy nowadays for your laptop still has graphite as the anode material. Can either be natural graphite or synthetic graphite. What else do you need? You need a lithium conducting electrolyte. So you need an electrolyte between these 2 electrodes that allows the lithium ion to move. And this is typically some organic solvent. There are many, I'm not going into the details here, and some lithium salt dissolved in it. What else do you need? You need a separator. This separator is sandwiched between your 2 electrodes, and it prevents the electrons to short circuit, but it allows the lithium ions to go through. The separator is some polymer, typically like polyethylene, for example, a very thin layer or film of this polyethylene. And once you have such a device, you can connect your 2 electrodes to an outer power supply. And if you apply a potential difference, you create an electric field. And if the electric field is strong enough, your mobile charge carriers will start to move. For example, in this way, that the electrons move through the outer circuit from the cathode to the anode, and the lithium ions close the path and move in the same direction, but within the electrolyte, also from the cathode to the anode. If we have such a directional movement, we say we are charging up our battery. And once the battery is charged, you can replace the power source, connect there any load, like a simple light bulb, for example, and then reverse the direction of current movement. The electrons go now from the anode to the cathode, while the lithium ions move in the electrolyte from the anode to the cathode. If we have this direction of movement, we are discharging our battery. And then this whole concept, this can be found in very different geometries, but it's always the same principle, right? You can have cylindrical cells, you can have coin cells, you find prismatic cells or pouch cells on the market, but they all use and apply the same working principle. Having said this, I would like to talk about some future trends as I can see them at the moment, my best guess. Moving from lithium to sodium. This again comes to this picture that there is a supply gap and that there is a very high price for lithium, and also there's considerable carbon dioxide emission by mining or harvesting lithium. If we want to compare it very blatantly, and please just take it with a grain of salt because it's not so so fully blatant as shown here, but we can say lithium-ion batteries, they have critical, expensive, and toxic raw materials, while sodium-ion batteries have sustainable, inexpensive, and abundant raw materials. Now, this is not 100% true, but for example, lithium we can replace by sodium, of course, and I have already shown you the benefits of sodium. We don't need nickel there. So in a sodium-ion battery, nickel is not used. Also, cobalt is not needed. And we also don't have to use copper, but we can go with aluminum as the current collector on both electrodes. And this is also much more abundant than copper on Earth. Other advantages of sodium-ion batteries, except the difference in price that you can see here, is that they are less dependent on temperature. Sodium-ion batteries are claimed that at minus 20 degrees, they still retain 90% of the nominal capacity, while the best lithium-ion battery at the moment on the market, NMC, is down to 70%. So this is also an additional benefit of using sodium-ion batteries. In fact, there is already a producer for sodium-ion batteries. This is a Chinese company, of course, CATL. It's also the largest battery producer in the world. And they brought to the market in 2025 a sodium-ion battery called Naxtra, and this already for electric vehicle application. And they can retain 90% of the nominal capacity of the battery at minus 40 degrees temperature. So this is very, very well. The energy density with 175 watt hours per kilogram is comparable to state-of-the-art lithium-ion batteries, and they can run an electric vehicle with this sodium-ion battery for 500 kilometers, and they promise more than 10,000 charge-discharge cycles. So for an average use of an electric car, this would correspond to 20 years of driving your car. And if you think on the cars that you are driving, like what car drives longer than 20 years, usually all other parts in the car break down before your battery breaks down nowadays. Another trend that I can foresee is changing the anode material, going from graphite to silicon. Why? Because silicon has just such a higher capacity, storing capacity of lithium ions, around 10 times higher than graphite. It's not pure silicon that will be used in the near future because it has some issues, and I will not discuss them here. They are discussed often at scientific conferences, but it will be a silicon carbon composite material. And this is already available. This is commercially available. This has left the scientific labs, I would say almost 10 years already, and is now at the industry and at the engineers to be produced, and will, to my estimate, for sure come in the next generation of batteries. Now, the battery consists of many parts, not only of the active storage material. So if you replace the anode from graphite to silicon, you can expect an increase in storage capacity between 30 and 40%, which is quite something, actually. And then, along with this, there is also a trend on engineering side. So it's nothing to do now with material science where I'm working in. This is purely engineering, and this is how you assemble and stack your cells that make up the whole battery pack that you need in your electric car. And just by make this stacking more efficient and in a more clever way, you can increase the energy density by around 35%. And again, this Chinese company, CATL, demonstrated this in their Qilin battery. This is a lithium-ion battery, and they have an energy density of 255 watt-hours per kilogram. And with this, you can drive an electric car more than 1,000 kilometers. There is this WLTP procedure, which takes many parameters into account, and it lets you predict when you have this energy density in your battery, how far or how long can you drive your car. Now, let's consider these two options. You have the better packing, like in the Qilin battery, and you change from graphite to silicon as the anode material, which would give you then to this 30% that you get from the better packing, another 30 to 40% increase in energy density. So roughly 350 watt-hours per kilogram. This would then allow for electric cars that drive more than 1,400 kilometers. And this is foreseen by almost everybody in the field that this will come within the next years. The last trend I would like to discuss here is pushing the energy density. So this was short, medium. Now let's look at the long-term perspective. And this is just a quick overview of different technologies that are out there. You can see here on the x-axis the energy density in watt-hours per kilogram. And you can see there are two different kind of bars. You can see these blue bars. These are batteries that are confirmed, that are already existing, either on the market or working in laboratories. And then you can see arrows. And these arrows are what, to the best of our knowledge, we can estimate that with this kind of technology, how far can we push this technology in terms of energy density. And on top, you can see the common conventional lithium-ion batteries. The best in the laboratory have now already around 300 watt-hours per kilogram, but the material constraints, the science behind it would still allow to increase it a little bit more to 400 watt-hours per kilogram. Sodium-ion batteries, you can see they are now already also blue. So there are already batteries, of course, in the laboratory, but also on the market. And the possibility that this technology offers is similar in the same range as lithium-ion batteries. And then below what I already talked about is silicon as the anode material. Now you can go around, or there are already batteries around 400 watt-hours per kilogram energy density, but you can push this technology up to 600 watt-hours per kilogram. Another major step would be using pure lithium metal as the anode material. So you don't have anymore any host material that incorporates lithium ions or that converts them, but you have pure lithium metal there. And this would again push the energy density very much, up to 800 watt-hours per kilogram. There are already existing batteries, but not readily available on the market because there are still some issues with safety. You can imagine always when you have a lot of energy packed onto a very small room, it becomes dangerous. And there is some engineering handling that has to be solved before this can be in large-scale consumer applications. Then there is lithium sulfur. Lithium sulfur would harness the complex chemistry of sulfur chains, which would be very interesting on one hand because it also offers a very high capacity, around 650 to 700 watt-hours per kilogram. On the other hand, because we have such a high abundance of sulfur, which is mainly a byproduct of the fossil fuel extraction. But it would be very cheap and could be used efficiently, but the chemistry is quite complex. And as far as I know, there is not yet any commercially available lithium sulfur battery on the market. It's in the laboratories, they are experimenting with it, but so far this complex chemistry has not been fully solved satisfactorily to bring it to the market. And then finally, we come to the holy grail of battery science. This is the lithium, or you can also say sodium air battery. This consists of a pure lithium metal anode, and the counter electrode is just the oxygen in the air that is surrounding it. This would be such a nice and elegant way, and with this kind of technology, theory predicts that you can push the energy density up to 1,200 watt-hours per kilogram. Now with this, then you are almost in the range of, or in the energy density, what fossil fuels like gasoline offer you. And you can imagine if you have the same energy density, but the engine that works 4 times more efficient, how far you can then drive your electric car before you need to refuel it, right? Okay, with this, I would like to come to the last part of my presentation for today, and this is the battery research that we are doing here at the University of Innsbruck. And one focus of our research is to go into this direction of the environmental and social responsible battery production. And we experimenting and working on producing an organic battery. Why do we think that this is a smart idea? Because in the ideal case, we could then mimic such a closed loop cycle. So we extract all the materials that we need to produce our battery from nature, from plants, for example, take sodium that is very abundant, and then build our battery. And once we are at the end of the lifetime of the battery, this can just be recycled and converted back because it's by nature biocompatible and bioconvertible. One class of materials that we are actively working on at the moment are small organic pigment molecules, like for example, anthracenones. We investigating 2 different types of anthracenones in terms of their substitution patterns. We're using amino and hydroxy substituted anthracenones and testing them for their battery performance. They have these 2 carbonyl groups there for all of you who are chemists, and they store lithium ions and sodium ions via these carbonyl groups. And for example, the hydroxy substituted anthracenones, they can be found into the barks and roots of many plants. And the amino substituted anthracenones, they are already heavily used as colorants, for example, in inkjet printing or also for dyeing your clothes. Typically, these amino anthracenones are used. So this is cheap and non-toxic material that is available. Another class of materials that we investigate are parylene, and they show really outstanding performance. So I'm very fond of this type of materials. And usually when I present the research results and talk about this at scientific conference in the battery community, they say, yeah, well, it's very nice that you have organic materials, and then in theory you convert them back because they are biocompatible and bioconvertible, but actually forget about this. Because if this is organic, if this can be decomposed and so on, you will not make a battery that lasts very long. Maybe 100 cycles or so, but then everything breaks down. So we in our laboratory, we built such a symmetric cell, which is that you have on both electrodes, you have the same active material. So on both electrodes, we used these parylenes. This is something that you do very often in science when you want to characterize a material because you just want to know the performance of this one material and not all the other side effects that come with it or with the different kind of counter electrode. So we built such a symmetric cell and we cycled it in our laboratory, and I'm not going here into the details again of the chemistry and curves, but it cycles very well. What you can see here is 1,500 charge-discharge cycles. Now, for all of you who are not familiar with these plots, this is what we typically use in battery research to show the performance of a material. You can see here on the y-axis the specific storage capacity in terms of milliampere hours per gram of material, and on the x-axis there are the cycle numbers. And each dot in there, like each black dot, corresponds to one charge and discharge cycle. And there is a red dot on top, which tells you the efficiency, the Coulombic efficiency in this respect. So with what efficiency can you put your charge into the battery, and with what efficiency can you take it out again? And here you can see we cycled this symmetric cell for 1,500 cycles. The green dots, they represent a faster cycling, so less time to store the energy and take it out again. And this even increased the capacity. So this was quite interesting to see. And for all these 1,500 cycles, the efficiency is almost 100%. Now, of course, we did not stop there. We continued to cycle this material. And what you can see here are 3,500 cycles. And we continuously increased the cycling speed. So the time it takes to charge and discharge the cell. Again, we continue to cycle this battery, and what you can see here are almost 10,000 cycles with no loss in capacity. Of course, the faster you charge or discharge your cell, the less capacity you can store in there. This is so with all batteries around. And at the end, what you can see here in purple, we charged our battery in 2 seconds. So you can imagine if you drive your electric car, you plug it in 2 seconds, it's fully charged. Now, this would be very nice. We also did not stop there. We looked what happens if we just store this battery. This is the so-called storage life. We investigated. So we unplugged the battery, we put it into the shelf, and we were waiting for 1 month. And then after this 1 month, we just lost 13% of the initial capacity. And we stored it longer. We kept the same battery, so this is still the same battery, for 1 year in the shelf, and plugged it back in again, and it retained 88% of its efficiency. And at the moment, we have more than 20,000 cycles for this symmetric cell. Now, if you remember back what the company CATL claimed, if you have 10,000 cycles, this would correspond to a lifetime of your battery car for 20 years. This would now correspond to 40 years of battery lifetime without much loss or any notable loss in capacity. So this is at the moment really the best working horse, so to speak, that we have in our laboratory. And by the way, this is an aqueous battery. This is an organic material. This is bioconvertible and biocompatible. But we are not only working into this direction. We have at the moment an ongoing project, FWF project, where we look at the material silicon carbide. So this is another attempt of making silicon usable because of this theoretically high storage capacity that silicon offers. So we are investigating this and the various storage mechanisms that are not known for this type of material up to now. And we also team up with companies. We have at the moment an FFG project running, and there we look at the thermal management of batteries. And basically we look at what type of chemistry and chemical reaction triggers what thermal response. And this is very important for battery producers because the temperature often limits the performance of the battery. And if you understand the chemistry, then you might even be able to predict how the thermal response will be, and the company can then integrate this in their battery management system to run a state-of-the-art battery more efficiently. I should not tell too much because the company is involved. This is not state-of-the-art battery. This is a sodium-ion battery that is intended for going to the market. So hopefully, if we do a good job, the company makes it. There are other projects, ongoing collaborations within the frame of this university with Professor Heidi Schwarz. She is an inorganic synthetic chemist, and also with the theoretician Professor Thomas Hofer. We are at the moment teaming up to look at the possibility to find a completely new class of material. These are so-called metal organic frameworks. Also, I will not go here into detail, but there we try to join together and hopefully get a big project funded for the next generation in battery materials. Also, I'm collaborating with the biologists, with Andreas Wagner, and there we really look into this direction, how well and how good can you decompose and compost and degrade our organic batteries, right? That really can show that we can close this cycle, converting all the materials back into nature. And the biologists, they have all the tools and all the means to look into this direction. And then there is also at the moment a very big consortia formed with many university groups and also companies involved in whole of Europe. And in this, we try to really extract all the materials from nature and build the battery. And this is intended for a big European funding proposal. It has already been submitted. First time was rejected, unfortunately, but we will try it again one more time. Now, with this, I'm coming now to the end of my lecture today and the closing remarks. For all of you who want to go more into the details, want to learn more about different battery technologies, about the physics and chemistry behind this, but also about other energy technologies, we just designed now a new lecture, which is called Advanced Materials for Energy Conversion and Storage. In there, we are 3 people who share this, 3 lecturer. There you will get information about batteries from my side, of course, but also about solar cells, about fuel cells, about electrolyzers, and so on. This was now taught the first time in this summer semester within the master's program of functional material sciences. So for all of you who want to learn more about this topic, you can, or you are welcome to join this lecture. With this, I would like to give thanks to the chair of our institute, Professor Julia Kunze. I would give thanks to my research team. They do really all the hard work in the laboratory so that I can stand here and show you then these nice results. And of course, I also have to give thanks to all the funding agencies. Without their money, this would not be possible. And to all the company partners that collaborate with us at the moment. And last but not least, of course, all of you I would like to thank for your kind attention.
So, wow, thank you very much. That was really fantastic. So, and also thank you for the announcement for the lecture. Maybe for some of you, it's interesting to join this lecture in future. That's highly interesting. Yeah, thank you. And now we can start the Q&A session. So if you have any questions, just raise your hand and I'll come over with the mic that also the online participant can understand you. And if for the online community you have questions, please type in the chat. We'll read the question and then you can ask, you can answer to those questions. Yeah, there's one question up there.
I wanted to ask, how long did it take you to create the recycling battery? And also, I didn't understand, the main element is sodium and the others from the recycling battery.
Yes. Sorry, can you repeat the second part of the question? I did not get this one. The first one was, how long did it take us to cycle this battery? And the second was?
The main element is sodium, right?
The main element of this organic battery that I showed you.
Yes. And
okay.
The others, what are like?
Okay. Yeah, thank you. So the first question, it took us more than 2 years now to cycle this battery. I mean, 1 year was just storing time in the shelf. so quite some time. And we have to be lucky always, because there can be some power outages and things like this, and then your measurement is destroyed. So this was a lucky shot also in this direction. The main material was not sodium. Sodium is the ion that is used to more or less close the cycle in the electrolyte, and then is then stored in the active material. And the main material was this parylene, this parylene tetracarboxylic diimide that I showed before. So this was the active storage material that then takes the sodium, and by this uptake stores the energy.
So we have two online questions. The first one is, I might have missed it if you talked about them before, but what about carbon batteries when compared to the previous types?
I have to be honest, I'm not fully sure what is meant with carbon batteries. I mean, as active storage material, carbon in form of graphite is of course heavily used. This is the state of the art. I'm not now aware that carbon can be used as the ion that is moving in the electrolyte. Does not make much sense to me. So maybe if there are some additional information, what is meant with the carbon battery. Could also be that there is a battery technology that I'm not aware of. I mean, this is also possible, but
okay. So, and from the same person, he's going on. And what about battery waste when talking about lithium-ion batteries? And switching usually takes ages and production accumulated compared to combustion engines, environmentally speaking.
Yeah,
the main argument here I hear against electric cars is how bad for the environment battery production and batteries after their life cycle are, and they don't last long enough. What's your stance on that?
Thank you very much for this question. It's a very important question. And this is also what I wanted to point out in my presentation with this environmental and sociable responsible battery production. Now, recycling batteries is very important, especially with this technology that we have at the moment. With the rare earths, with the cobalt that is in there, with the lithium that is in there. And there's a lot of work going on into this direction. In fact, there's one very nice study that showed if you take the cathode material and then you just grind it up and mix all the materials together after the cycle lifetime, and you do it well, and you cast then this as a new slurry on the electrode, that it even works better than the original material, because this is then just a better way how to mix these materials, that you have a more efficient charge transport. But this issue we also going to address with this organic batteries that we are researching on that are bioconvertible. So then this waste issue will not be a problem anymore. Also, the materials are abundant, and so is it with sodium-ion batteries. Now, when I was talking about sodium-ion batteries, maybe a few words on this, I was not saying that sodium-ion is going to replace lithium-ion somewhere in the future completely. There is such a huge demand for batteries that I think that both technologies will develop side by side. But for many applications, especially for large storage applications, I can predict, due to cost issues, due to issues with the materials that are used, that at some point the sodium-ion battery will be used more heavily than lithium-ion batteries.
And another question from another person. Hello, I have a question. Can the other course you just showed be studied by anyone from any department? Does it require any pre-requests?
Yeah, it's a master course, and I think it can be chosen freely within this ECTS of this interdisciplinary competenzen that are around. So I think there are no other, like it's not in the standard chemistry classes, it's in the functional material sciences, but within this interdisciplinary competenzen, you are free to choose what master course you want to take.
If you're a student from here. It's not a Aurora course. It's just if you're a student from the LFU.
Yeah,
then
yeah,
it's
this,
okay.
at the moment, yes. I mean, it just started, so this was not the first time this lecture was held, and I'm very open to any future possible format that we broaden it, that more people can join. I think it is very relevant in these days and also very interesting. So, yes.
And does it need some pre-knowledge of chemistry to have the knowledge beforehand?
Well, some pre-knowledge would be good. I mean, it's not absolutely necessary. We start with each technology from the fundamentals, and yeah, I think, I mean, at the moment it is designed in this way that you have a bachelor degree in chemistry or physics or material science or related into this direction. So this is somehow on this it is based. Yeah, so this is of course helpful if you have this.
Yeah, so questions, please. Maybe a question from my side. So all you talked about in this lecture looks fantastic. It was always only advantages, but be honest, what are the disadvantages? Because if there are no, I couldn't understand why it's not widely used or widely researched all over the world. It's that's what we need urgently. So there must be some disadvantages.
Well, there are actually not many disadvantages. And honestly speaking, I think that we in Europe completely missed this development. I was, for example, talking to a scientist at the conference who works at this Chinese company, at the CATL company, at the conference in Italy. And we were talking after his presentation, and he told me that the company alone employs more than 10,000 scientists who are just working and developing on batteries. Now, if you take whole Europe together with all the universities, you never can get these 10,000 scientists working on batteries. So maybe it's also an issue of the past, right? That we in Europe are very strong on combustion engine. The industry, the government, and so on go all into this direction. And unfortunately, we know it. We are very conservative. So changing existing structures is very difficult. But it's happening. I showed you the figures from Norway, for example. Also now in Austria, I myself drive an electric car and would never go back to the combustion engine. So there are not really disadvantages that I see. I mean, the charging, of course, is still an issue, but it's getting better from year to year. This Killeen battery, you can charge up to 70% within 10 minutes, which is not that long anymore, and it will get much better in the future. I'm sure on this. They're also now, again, in China, they're experimenting that you go with your car to the loading station, and then there comes a robot arm. It takes out the total battery, plugs in the full one. It takes less than 1 minute, and you're ready to go again.
Perhaps I missed it. A question from my side, but is there any disadvantages about weight, about the security, about that you can how you can form it, that you can put it in a car or for use it for different, or is it the same if you have a lithium or if you have a sodium battery?
This is, thank you for the question. This is actually the same. So you will not recognize any difference in geometry or how you plug in your battery finally. So the difference is in the chemistry and in the materials that you use. But this is all everything inside a black box, if you want to say it, that outside you don't recognize any differences. And also you must imagine that this whole process that I showed you with the 2 electrodes, with the separator in between with the electrolyte, this now takes place in a foil that is 10 micrometers thick. So within this 10 micrometers, everything happens. And also maybe related to this question, I can elaborate a little bit more. If people think of battery, then usually people think of something that you do in your garage where you have your beaker and your electrodes in there, and then some light is coming out. No, we are talking here now at the a failure to safety ratio of 1 part per billion. So you can imagine you have all these electrodes in 10 micrometer thick layer, and the failure ratio is 1 per billion, so the same as semiconductor industry. So we need very precise, highly accurate manufacturing for building batteries, and this is also why it is so difficult to build up a complete battery plant. That there are unfortunately many examples in Europe where they tried to start with battery production and then filed bankruptcy within 2 to 5 years.
What was also very interesting in your presentation, the energy density was rising year by year. So they becoming always more lightweight from year to year. And that's for traffic very important, the lightweight construction. Do you foresee that in future the way we will build cars will change completely? Because now they are really heavy vehicles, and in future might be they will be lightweight, and then we can change the security, we can change the complete construction mechanics. Is there still some way for even lightweight construction in the future?
Yeah, lightweight is actually not so much an issue in the cars. It's more the volume that you have available, and then typically you just pack in more batteries that you increase the range. At least in the moment, this is this direction. It's more in terms of space application, where each kilogram really matters a lot, where they go for lightweight. But unfortunately, this is just my personal opinion now, I think we should reconsider completely how we produce cars. I mean, it does not make sense that we drive a 2.5 ton monster around to buy in the shop 1 bottle of milk, for example, and get something like 1 kilogram back home. And for me, it's very unfortunate that with this transition now to electromobility, the car producers, of course, out of the demand from the market, but they make the same mistake again that they have done with the combustion engine, that it always has to be bigger, more comfortable, and so on and so forth. So this is a wrong development, especially if we look into the global crisis in terms of global warming that we have at the moment, and that we need a very fast transition away from the combustion engine.
Yeah, further questions? There is no in the online. No. Okay. Yeah, then I would say thank you very much. Thank you for this brilliant presentation. Thank you for coming. Thank you to the online audience. And yeah, this was really the last lecture of this summer semester. You're highly welcome also for the winter semester. We will have new lectures, new topics in the upcoming winter semester. If you are interested also in these, you can join or yeah, look online or the recordings. And don't forget to upload your task on the participant folder. You still have enough time to do so. No hurry, but yeah, just don't forget if you want to get the credit points. If you have any questions, don't hesitate to contact yeah, Ingo or me. Yeah, and then maybe we'll see next semester. Thank you very much for coming. Goodbye.